These are the only slides about today, but we will go through during all the lecture because there are some useful images and we can understand easily a lot of stuff. So I just present briefly myself. My background and also my heart is still for theoretical particle physics. I'm a theoretical particle physicist. Everything started with my curiosity about the deep understanding of nature. Then I did a PhD in theoretical physics, working on quantum information theory, which is really a fundamental theory behind many theories in physics. But during my PhD, I passed a period in the United States, in San Francisco, was 2015, and there everybody was talking about machine learning and deep learning. In Europe, not yet, but in San Francisco, everybody was talking about deep learning. So actually, when I went there, I was in a aperitif, and I asked to a guy, but what is this kind of machine learning that I heard about? And this guy told me, I remember, told me, no, machine learning is cold. Here we are doing deep learning. Deep learning. And so I got excited this branch of AI, and I did a postdoc in deep learning applied to computer vision on nanoscience, to recognize nanoscience images 5 years ago, roughly. And I worked for 8 months just to build a classifier in TensorFlow, a classifier of nanostructure, images of nanostructure. Today, you can do the same task, not in 8 months, but in, I think, 20 minutes. Just to let you understand how fast deep learning has grown in the last years. Really impressive. Really 20 minutes, not me, but you, without knowledge about anything. From 0 in 20 minutes, you can do today what I have done in 8 months, 5 years ago. You see, this is just to tell you. Then I was hired by Samsung AI as a research scientist, and I specialize in natural language processing, which is my main expertise, as I told you before. And now I'm a lead AI scientist at Pi School, which is a startup, which is a bot educational startup. We are running a school of AI, but we are also working on impactful project with European foundings and stuff like that. And I lead the AI team. We are very small. We are so small that I'm also leading the communication team, so posting on Twitter, LinkedIn. I'm leading also the communication team, so that's an adventure. And I'm also a lecturer in a couple of places. One is the Master in High Performance Computing held in Trieste by SISTA, which is where I did my PhD. SISTA is an Institute for Advanced Study in Trieste, theoretical physics, mathematics, and neuroscience. ICTP is a very beautiful place. It's the International Center for Theoretical Physics. It is a UNESCO center, so from the United Nations, and they are doing research and education for developing countries. And also, I'm giving a couple of courses at Bicocca University in Milan about generative networks, which is a branch of deep learning for PhD students. And recently, I also become a digital EU ambassador, which are 20 people in Europe, selected, because they are working in tech, but also on social network. And we are helping the Digit Connect branch of the European Commission to spread on Instagram, on Twitter, and whatever, what the European Commission is doing in digital and tech fields. Okay, perfect. So the goal of today's lecture, we just have one day about deep learning, is to learn how to build a custom deep learning model from scratch, especially for images. When the model is done, okay, so we are not focusing on building the most advanced herd observation tool, but we are focusing on really coding from scratch a neural network. When the model is done, you can integrate it with all the machine learning techniques and the data science pipelines you have learned the previous day and you can learn in the future. Some warning, apart from these introductory slides, this lecture, sorry for the title, I must correct it, I wrote it before, will be hands-on. And in one day, we cannot cover mathematical and statistical foundation of deep learning. I must say it because sometimes I give lecture to physicists and mathematicians. They are really, they want to understand everything. So if you miss some mathematical detail, they are there to tell you, yeah, but you didn't tell us about, did not demonstrate. Okay, so it's a warning. So many details are skipped. The lecture might appear tough for somebody, for someone, but don't worry, everything is yours, and you can then study it by yourself tomorrow, next week, next month, okay? So let's start with a warm introduction. I'm sure, and I know that also in the previous day, they talk about it. We have several problems in nature. Some of them are linear, so easy. You can really split, for instance, here we are talking about classification. You can split them very easily, just with a line, 2 parameters, you see. Very easy to learn, very easy to solve. Then we have non-linear problem, you see, quite similar, but we have a dot, a blue dot on the green side, so there are no lines that perfectly separate green and blue dots. These are non-linear problems. So you see, attempting with a linear approximation, we yield reasonable results, but will not be perfect. So you can solve it with a linear approximation, but you will have some errors, you see. It's not perfect. Then there are highly non-linear problems, like 99% of problems, not only in physics, but in life. So highly non-linear, you cannot at all model them with linear function like this one. And they are very unstable. Small input changes can result in counterintuitively large change in the output. So it's really a mess. Deep learning was developed to solve or to tackle this kind of highly nonlinear problems. I can give you a couple of examples of highly nonlinear problems. Maybe the most nonlinear problem, that's the reason why it's also one of the main challenges of AI, is language. I can stay here 2 hours just giving you example on how language is sophisticated, but I will not do it. Just a very simple example. It's supposed to have a task and discover who is from Svalbard, person A and person B. You see, we are very smart as humans. We are able to understand very quickly language. But computers are not so smart as we are. And think about to teach a computer how to distinguish who is from Svalbard. So there is a nice weather in Milan in winter. It's like our summer, I feel at home. So for a computer, it's not easy to understand that this is the guy from Svalbard. And instead, this is a guy maybe from me, from Rome. I had the weather in Milan during winter, it's freezing cold, I want to be back home. Maybe this guy is from Sicily. You see, we understand it immediately, but for a computer, it's a very difficult task. You see? So deep learning it's really useful to help computer understanding this stuff. We are not done with language understanding, we are very far away, but I really can tell you that in the last 3 years, thanks to this technology, which is called transformer, the mechanism at the core of transformer, it's called the attention mechanism. Really, we went not close to fully understand language, but really we had several breakthroughs in this branch of AI. 3 years ago or 4 years ago, I had the opportunity to give a TEDx talk about AI and creativity. I'm still convinced about what I have said in that talk, but I was not realizing how fast AI, in particular on language, has developed. So really, it's unbelievable. On one side, and that's also the reason why this is very important, I decided to put my effort on impactful application of AI. So to understand climate, to mitigate climate, for social challenges, because I think that AI could be an issue if applied not in the wrong, in the right sectors. You see, that's my philosophy. Another, more related to our lecture, another very complex problem, for instance, with images or unstructured data for some we can say that also images are unstructured, and highly nonlinear, like text. For instance, teach to a machine to recognize that these are clouds and these are icebergs. It's not an easy task, you see. So that's why deep learning, deep learning can deal quite good with highly nonlinear data, and that's why we use it in language and images. You see? So here, very simple slide to tell you that, you see, this is, deep learning is just a nonlinear engine to, in this case, do classification. And deep learning is an engine that couples many degrees of freedom, that are what people call parameters, what we are going to learn during training, couples many degrees of freedom with nonlinear functions. Okay? And let's just briefly understand the basic mechanism in learning. Now, here in these images, what is represented is what people call a linear layer, or a linear, sorry, a fully connected neural network, which is composed by many linear layers. So it's the simplest model in deep learning. You see, many linear layers, and fully connected means that each neuron on this layer is connected with all the neurons in the previous one. So here it's let's say layer 1 and layer 2. You see, there is, this guy is connected with these blue dots, this guy is connected with this one, and the linear layer are the basic, most basic layer, and let's say fully connected layer, they are also called dense layer, is the simplest solve specific tasks like images. Okay, but recently, thanks to transformers, people somehow reorganized the linear layer, the fully connected neural network in a clever way, and inside a transformer, they are just fully connected linear layers. So the simplest one, but organized in a clever way. So no convolutional neural networks in a transformer. So just to tell you that linear layers and fully connected neural networks are really a powerful tool still. Okay. So you see that the basic mechanism. Okay, you see, deep learning, it's really just matrix multiplication coupled with nonlinear functions. So, what does it mean? We have these two neurons, and then we have a second layer, the yellow one, And these guys are just, you see, a linear combination of these two inputs, these two values, with some weights. These weights could be represented in this matrix. This is just matrix multiplication. You see, this guy by this guy by this gives this. Tac, 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 tac. See, just linear, just matrix multiplication. But if you couple many matrix multiplication, it's just another matrix multiplication, which is a linear operation. So with just matrix multiplication, also if you couple many of them, you are not building a non-linear engine. You are not building a non-linear engine. So that's why people, they were clever enough to understand to put here, you see, a function which the only requirements, I hope there are no mathematicians here, the only requirements is that must be non-linear. Then it's not exactly true because this function must respect some basic mathematics properties. For instance, must be differentiable, so some details. But at the moment, we can say that, you see, we can use a nonlinear function. A nonlinear function could be, we will see then some example, but really also a cosine, sine, or tangent. They are very simple. You learn them, at least in Italy, during high school. So very simple function. So here is the magic mechanism. Matrix multiplication combined with nonlinearities. This is one of the simplest nonlinear function, which is linear here, but not here. It's called the real. It's one of the most popular. Rectify linear unit. And you see the transformation is very simple. This is, let's give a very simple example. If you multiply those guys, you obtain this vector. And nonlinearities, it's applied later. And if a number, if an entry is less than 0, you put 0. This is just gives you already nonlinearity. You see? You see 7, you put 7, 6, linear, you put 6, minus 2, 0. You see, very, very simple. So this is the basic mechanism in the architecture. Then you need to, but you see, the secret are these parameters. At the
this question.
yeah, sorry.
Why is it okay to basically remove negative information because you're setting it to 0?
Yeah, because you see, I'm just applying a nonlinear function to the result. You see? And there is a mathematical recipe that tells you if you apply whatever nonlinear, okay, not really whatever, but okay, almost whatever nonlinear function, you obtain a nonlinear engine. And so you see, this is a nonlinear function because it's linear here, but not here. If you are considering all the spectrum of number of real numbers, and you apply this function, this breaks linearity. You see, breaks linearity because linearity is here, no linear. Here, linearity is broken. So it's enough to build a simple neural net. But you see, this is really the source. It's really the main concept. Then there are many technicalities, but as a physicist, I always search to understand the simplest one. Then all the other stuff are just engineering the basic concept.
And how does it normally work? Because now you have like the expectation function that you choose, but you can choose different functions depending on what you want.
Yeah.
But could you also choose different functions for each layer, or is it every layer has the same expectation?
No. We will see later. In general, I must say that deep learning today, it's not a mathematical well-defined theory. it's like quantum mechanics in the 20s. So you try stuff and see if it works. You see, there is no theorems today that tells you you have a herd observation problem with satellite images from Copernicus. So you need to use this, and this. There are no theorems, you need to try. But there are some rules and feelings that works. Okay, and one of them is that you can choose whatever activation function independently, layer by layer. So let's say tangent, ReLU, leaky ReLU, which is a modification of ReLU, and whatever. But if your final task is a classification, for instance, so classifying images, the last layer must be a softmax activation function. Because of softmax, we will see later, is a specific activation function that was built, invented to solve, to classify. So to answer you, you can, yes, choose whatever you want, but you are, the last layer, you are constrained depending on the task you want to do. So, okay.
And it has to be the scope.
For classification, we will see later.
Because it's a two-dimensional.
No, okay. If we have just two classes, we have two possibilities. If we have a binary classifier, we have the possibility to choose a softmax, sigmoid. Instead, if you have more than two classes, so you know, clouds, iceberg, and ships, you must choose a softmax.
Okay.
Okay, but we will see later. To answer to your question is just that yes, you have freedom to choose almost whatever you want. Try what setup is working the best, but last layer in general depends on your final task. Okay. So you see, this is the general mechanism, but we haven't mentioned anything about learning, which is one of the main points in deep learning. That's why learning. But it's very simple. I told you we have each layer is connected with this weight that somehow at the beginning are random initialized. When you start to build a deep learning model, at the beginning, this model is not trained. So these weights that connect all the neurons are random initialized, random setup. You see? Perfect. The idea is that this will become weights that their role is to weight how important is this neuron or this one. Okay. Learning in machine learning, but especially in deep learning, means try to find out the best value of these weights in order to understand layer to layer which are the most important connection. So I will give you a very simple example. Suppose we have some images, blue and green. I don't know, the task is to recognize from a satellite if the picture is of the ground or of the sea, of the ocean. It's very simple. We give these images to the network, and we say that these images are forward passing the network. Then we will see how does it work, but just give you an idea. And the network at the beginning, it's random initialized, and its outputs will be random. So for instance, we have a blue, green image, and the network is random initialized, it's not trained yet. And we'll give you green, blue. So the opposite. You see? This could be at the beginning, the first step of training. But the true value are blue, green, opposite. So we can compute what is called a loss function. There are many of them, but you can just think about loss function is counting the errors. You see how many errors the guy is doing. And so you compare the true value, blue, green, with green, blue. 4 errors. We don't like it. Too many. 4 images, 4 errors. It's not. So the idea, it's very simple. We need to minimize the loss function. Okay. But what does it mean to minimize the loss function? Is a function of what? This loss function is a function of the weights. You see? So the idea is that we can tool these weights, change them a bit, and this in mathematics it's called gradient derivative. So tune a bit in which direction? In the direction of decreasing the error. You see? Very simple. And so you see, you compute this derivative, okay, and you change a bit the weights. You see, here were somehow randomly initialized, and now I'm tuning them a bit. This is called backpropagation. And the secret form, not secret, but the most relevant formula in deep learning is that the new weights is nothing else than the old one minus the correction of this derivative. The correction is weighted by not a parameter, but this is a hyperparameter, then we will distinguish them. It's called the learning rate. You see? Maybe I can draw something here. I want to give you every function, also the loss function. If you remember in high school, you can compute the minima, maxima of every function with derivatives. No? Very simple. So if you have a function, maybe I can draw it here. No. Okay. Well, it's this way. No. It was working before, actually. Sorry? Ah, okay. Ah, yeah, that's true because it's on the. Okay. Thank you. Think about you have a function. And this is the loss function. Okay. And I want to remind you that depends on the weights. W. Okay. Many weights. So it's a very complicated function, not just in 2 dimensions. You can have many weights. But okay, in general, a function has some absolute minima and some local minima. And the learning rates helps you to discover the minima of the function. So at the beginning, when training is not yet started, the network is randomly initialized, and let's say the loss function has a very high value, because you see 4 errors. So very high value at the beginning. So maybe it will start from here. Okay, very high value. The idea is to compute derivatives to find the minimum and to apply some correction. If the learning rate is very, very high, you are applying a huge correction for each step. We are moving in this way. One step, another step, so you go in the right place, but then the next step you could move away, for instance. Instead, if you have a smaller learning rate, you can go with shorter steps. Okay? You reach a local minimum, but then you can escape from it and going down here. And then when you reach the absolute minimum, the step, the learning rate is so small that you cannot escape anymore. You see? So, in deep learning, not only the learning rate, but we have several hyperparameters. Hyperparameters are those that you set up at the beginning, and they are not learned during the training.
I have a question
Yeah.
about this learning rate. Is this something constant? I mean, is that
Is it something?
something constant? Is how big is this? Do you reduce them like at the beginning? Maybe they are
Okay.
low, and then reduce them to get precise.
In general, when you start with a very simple model, it's constant. And during training, you maintain the same learning. But it's not true in more advanced algorithm, you will see later. You can change the learning rate to increase or decrease during training. But this changing is not given by training, it's not learned. It's a function that you can decide a priori because you think that it's a good way to module this learning rate. But it's not learned during the training. In general, in 99% of algorithms. Then there are very sophisticated models developed by DeepMind, Google Research, that some hyperparameters that today we call hyperparameters are learned.
So
But I don't want to talk about it.
just one
Yeah.
comment. So I guess it's about the optimization of the hyperparameter.
Yeah, we will see, we'll talk about later. But you see, optimization of hyperparameter is an optimization, but it's not really learning in the way. So we are not learning through the derivatives of the loss function. There are other techniques. Okay.
Would you say that cost and loss function are the same?
Sorry, goes.
Like I learned before about cost function. Do you think it's the same?
Yes, it's the loss function. Sometimes it's called the cost function.
Okay.
Yeah, sorry. Yeah, it's the same. Physicists love to call it loss function or Lagrange, sometimes Lagrange. Lagrange is not very used in machine learning sector. But cost function is synonymous. Okay? So perfect. You see, starting from scratch, counting errors, trying to minimizing errors, tune parameters in the right direction. So hopefully then we can, you see, decrease the number of errors. You see this guy flipped, and we have now 2 errors. We tune again till 0 errors. You see that the weights are changing here. You see? We are tuning these weights. I remind you that the loss function is a function of the weights. We are tuning them, so loss function is changing till we reach 0. We will see later. Now think about, really now, the main goal of this introduction is to give you the overview. Then we will start with technicalities. There are many, but the overview is that you have a function. A function is a function of some variables. In this case, are the weights, and taking the gradient, so the derivatives, but it's better to see the gradient because we have many variables. Taking the gradients means doing derivatives of a function to search what the minima, like in high school. It's not even I don't know, your bachelor degree in mathematics and physics engineering. Already in high school, we were taking derivatives. Okay, so this is the main idea. Okay, is it clear? The chapter when we take derivatives, gradients of the loss function, it's called backpropagation. Okay, we'll see later. But backpropagation, it's really very, very simple. It's nothing else than the chain rule in derivatives. So if I'm taking the derivatives of the loss function with respect to this weight, I need before to take the derivative with respect to the waves, and then the other one. You see? Back propagation is the chain rule. If you write on Wikipedia chain rule, derivative is it's this one. Think about this is a layer function f, and this is function g. And we want to take the derivative with respect to this way. Okay, you can do. See, the loss function somehow is close to f of g of w. You see, because you need to pass through this layer. Can you see? Oh, it's too small. It's too small. But if you want to take the derivative of the loss function with respect to this wave, is nothing else than the derivative of f with respect to g, and the derivative of g with respect to the waves. So this is called the chain rule. You see, is it clear? This is called the chain rule in mathematics, and people from deep learning call it back propagation, because we are going back in derivatives. You see?
But then like in forward pass, roughly the data is going from left to right.
Yeah, no, exactly. Okay, in forward pass, it's forward from left to right. In backward, data is not flowing. What is flowing is the derivation. Okay, perfect. How can I cancel everything on the network?
The thing to raise the physical thing.
Ah, okay.
On your left.
Yeah,
This one. Wow. Wow, it's beautiful. It's really beautiful. Wow, that's good.
So there's an example, this subsidize linear and not propagation. This is one subset of the type.
Okay, sorry.
We're just trying to understand if this is a general aspect or if this is a specific example of this back propagation algorithm.
No, this is a general. You can use it on convolutional neural network transformers. It's a general. Okay, I here it's drawn a simple neural network just to keep track of everything. But this forward pass and back propagation is very general in supervised, in a supervised and also semi-supervised setup. If we are talking about reinforcement learning, or we are talking about clustering, other stuff. Today, we are talking about supervised learning, deep learning. So this is a general setup in supervised deep learning. Okay, is it clear? I was too basic because I'm slowing a bit down with trying to let you understand, but I'm too simple. It's fine. It's fine. Okay. So you see, we learned these weights. Okay. So 0 errors, and we have here we end up with a trained neural network. You see, we have finished our job. This is trained, and now it's able to solve our task of gorilla viewing images.